Okay, so this is Psych 222. It is Monday, February 1st, and we are into Chapter 3. So just a quick recap of things we talked about in Chapter 2. We talked a lot about the experiment and different ways of gathering information in science. Talked about surveys and things like that, and some of the issues that come about with these data recruitment methods. But we concluded with a heavy emphasis on the experiment, that the experimental design is very, very important in science. And we mentioned that as we're going to see throughout the course, we're going to be talking about experiments a lot and how statistics are used to help us evaluate data from experiments and other designs, such as observational designs. In this chapter, we want to start talking about data in general and how to describe data. And then we get to summarizing data in terms of computing statistics on it, such as means and other measures of central tendency, as well as describing variability. So if I just motivate our discussion here, and imagine we have a whole bunch of data points. Okay, there's a whole bunch of data points. Could be people, could be products in business or what have you, anything we like. Maybe they're IQ scores. Okay, so those are all IQ scores. Well, if we look at this big bunch of data, this data could be in the thousands. Okay, it could be in the 100,000s, especially today with the notion of big data. Some data sets are absolutely huge. They're humongous. So we definitely need ways of summarizing the data. And in this sense, you can think of this as reducing the data. Okay, reducing data to some simpler summary. Well, oftentimes to reduce the data, we do things like graph the data, and we'll look at bar graphs and histograms and things like that. The graphs give us simpler visual depiction. So if I just draw a bar graph of data here, like this, where I have, say, product A, product B, and product C, and maybe these are sales for the different products, well, notice that this summarizes the otherwise kind of messy data over here. Graphs are useful, but we also want to compute summary measures on data. So if these are IQ scores, as we were just talking about, well, then maybe I get the mean IQ of all that data is equal to 90. Okay. If they are different prices for different products, well, then I locate the A products, there's a whole bunch of B products, there's a whole bunch of C products, and then I can graph it like this. So there's different ways of summarizing data. And you can think of that as data reduction in terms of a summary. There's advantages to doing that, right? One advantage is, well, we can interpret one number here instead of having to interpret tens of thousands of numbers. We can look at the bar graph instead of having to look at, say, 500 or 1,000 data points. So there's an advantage to that, but there's also a disadvantage when you reduce data, right? When you reduce data, you lose information, and there's no way of getting around that. Okay, you will lose information. The fact that I computed the sample mean here of 90 doesn't tell me exactly what this observation got, doesn't tell me exactly what this one got, etc., right? I'm losing information. So there's a cost to reducing the data. Same thing here, if I look at the products, well, I don't get to see every individual data point. So we need to have a compromise between those two extremes. And oftentimes the reasons for graphing data or producing numerical summaries will depend on the type of investigation you're doing and the reasons why you want to communicate these figures. So we'll explore those issues. One distinction to make here is between descriptive versus inferential statistics. And I think we're clear on this pretty much because we've talked about this. So there's my population, right? There's my population of information. And because the population is too big to study, right? It's too big and it's too expensive. There could be, like we say, thousands and thousands of observations. I get a sample on the population. Okay. Well, when I compute an average on there, so a sample mean, and I describe the sample with the mean, that's called a descriptive statistic because it's simply describing something about a sample. If I calculate the mean on the population, we're going to call this mu pretty soon. This average here on the population can also be considered to be a descriptive statistic because it's simply describing the set of data. Well, we distinguish that between inferential statistics. An inferential statistic is when I use the sample mean here as an example to estimate the population mean. That's an idea of inference. It's an inferential statistic because I'm using it to make an inference towards the population mean. So if I don't have the population and I'm gathering sample data, we often want to use that to infer something about those population figures. So that's where we're into inferential statistics. That's an important distinction to make. And you could read the book examples here, give more examples of inferential and descriptive. There's another good example there you can read up on. Now here's where we get to the problem of data reduction, right? Reducing the data down. If we look at this whole data on third grade scores, well, there's different scores for math, for reading, percent minority status, percent poverty. Well, that data is continued on the next page. So this is elementary school performance. And these are for different schools as well. Okay, so we have a lot, and we have our different sample size over here, which is the N. Well, again, if we look at that, boy, that data gets to be pretty big, and we have it by different grades. Here's fourth grade, and here's fifth grade, et cetera, et cetera. So we have a lot of data that at some point, you want to reduce that data down. Now, we ask very, very meaningful questions of data. There's a whole bunch of questions we can ask of all this data. For instance, are there differences in these scores between third grade and say fourth grade and fifth grade, et cetera? We could also ask questions like, are there differences between schools? Do schools have different math scores and reading scores by grade? So we see there's a bunch of questions we can ask of that data. And what questions we ask of data will be motivated by what hypotheses we have. What would we like to know about the data? So let's see. Well, you can reduce the data down. And if you reduce it down, you might have third grade, fourth grade, and say fifth grade. And in this particular set, you might compute things like means, right? There might be a mean for third, there might be a mean for fourth, and a mean for fifth. But then we also want to compute how much variability there is in the data. So, if I have a whole bunch of data points here for third grade, well, I can calculate the mean, but I also want to get an index of dispersion, right? How much variability is there? For instance, if we look back at our data a little bit, we'll notice that this math score is different from this one, right? Is different from this one. That's called variability or dispersion. So though we can compute things like averages, and we'll see we can compute medians and modes and other measures of central tendency, we also want to have a measure of how much difference there is in scores. And that we're going to see is going to be developed into things like the variance and the standard deviation. So lots of questions to ask of data for sure. Just a quick note on calculators, computers, and software systems. We will be using a little bit of R in this course, and R is a software language that's used primarily for statistics. And in this day and age, software is used heavily when analyzing data. It's almost used exclusively. People rarely do things by hand anymore, even though it's good practice to do it by hand. But the important point here is to recognize that you have to make sure that you understand what you're computing before you compute it on the computer. So, we'll look at examples of this, but there's a sample mean. I can compute a sample mean. Well, if I compute it on the computer and it reports a mean, it doesn't tell me what the actual statistic is. It just says it's a mean. It doesn't tell me that the mean is the sum of x over n. It doesn't tell me all the weaknesses and advantages of interpreting the mean. It doesn't tell me that maybe a competing statistic would have been better off than the mean. All of those issues have to do with understanding statistics and not simply being able to produce them on the computer. So that's something to keep in mind, that even though we're going to do some software stuff using some computers, it's most important that you understand what you're computing. And as you go further into research, you'll see that there's a whole bunch of different programs that can be used. There's probably about 100 different stats programs when you really gather them all together. Many of them you don't have to pay for, some of them you do. This is the one that we're going to be using at times in this course, the R computing language. But there's others as well. This one's very common in the social sciences. This one, SAS, is very, very common in business, and a few others. There's also another one called Python, which is a computing language, and it's used for a lot more than computing statistics, and that's coming into a little bit of vogue even when computing statistics. So there's another language. There's a whole bunch of them. The key point is that when you learn one of these languages, and I'm talking about the syntax of it, you can usually generalize your skills to other languages. And you'll get to the point where you can just pick up a software package as you go. There's another issue to mention here, is sometimes some software is better for certain things than other software. So this is where it'd be a really big mistake. You do not want to say you specialize in SPSS, or you specialize in R, or you specialize in JMP. The way you should perceive software is that you will use the software that best gets the job done. And sometimes that means venturing off into different packages. Having said that, most of what you'll ever need to do can be done in the R software package, because that is, of these, probably the best one. For instance, if you compute something in SPSS, well, you may be limited and may have to switch over to working in R. So why not just work in R from the start and get very good at it? Okay. But again, if you go further into research, you'll see that sometimes you have to switch packages and pick up new packages and languages as you go on. Okay, so let's describe data on a single variable. So these are graphical methods. Well, here's some data: income levels and salary. So here's some salary figures. And this is just indicating an arbitrary level for different salaries, right? So if we say you're at income level 1, well, then maybe you make less than 20,000. If you're at income level 2, you make 20,000 to 39,000, etc. Well, there's different ways of presenting this data. Here's one way of presenting it, and here's another way of presenting it over here. And you can look at the differences between the presentations. Notice that this income level over here is 20,000 to 40,000, whereas here is 39,999. Well, notice that if we present our data this way, we may not be sure which level to put the given data point, because we have 40,000 here and 40,000 here. Whereas over here, it's a little bit more clear because we've separated 39,999 and 40,000. So recognize there's differences in how you can construct things, and there will be better ways to construct these data summaries than others, especially when we consider intervals. The infamous pie chart. Okay, everybody knows what a pie chart is because we see them all the time. Let's look at a pie chart here. There's a pie chart. So we have different services. We have trade, manufacturing, government, construction, and so on. And these are, I believe they're percentages. Are they percentages? I believe so. Yeah, there they are, right here. So number of disabling injuries. So injuries by industry group. So there's apparently 3.4% in agriculture. Construction, as we would imagine, may have a few more in manufacturing, a few more, et cetera, et cetera. If we look at the pie chart, well, the pie chart, it can be useful in some situations, especially if you have the numbers in the pie chart, right? Because then you can see immediately that this one has 24.3 and this one has 19.3. But if you take away these numbers, imagine if the numbers were not there. It could be very, very hard to see which slice has the most information. For instance, imagine if I took away the 16.2 and the 14.9. I'm not that good that I could tell which slice is bigger, this one or this one, right? It becomes very, very difficult to do that. Now, maybe looking at it enough, you can probably figure out that this one's bigger, but it becomes really hard to make those comparisons. So if you're going to do a pie chart, oftentimes it's nice to put those numbers in there. What pie charts do not show, or what we're going to call a good horizon. So if I produce what we'll call a bar graph pretty soon, notice that in this graph here, if I just compare these two categories, so this is 16.2 and this is 14.9. Notice that I can just tell that this one's higher than this one. Even if I don't have the numbers, I can look at the horizon, right? And I can see one's higher than the other. Almost like looking at the horizon when you look at the trees in the forest, right? You're looking at the woods and you can tell which tree is taller because you can see that horizon. This is much more difficult because you don't get that visual horizon to kind of see which one's taller than the other. So we have to be careful with pie graphs. Well, there's some guidelines for constructing pie graphs. We're not going to go through the guidelines, and we don't have to know them. But the book does give a bunch of guidelines for producing different graphs. I wouldn't worry about them, though. You definitely do not have to memorize them or anything like that. This might be good for making a comparison before the switch and after the switch in soft drink accounts. So there's an example where there's a different market share between switching, I believe it was from Pepsi to Coke. So you can look at this as 38% to 42% after the switch. Comparing the pie slices like that can be useful to provide a before event and an after event. And that may be nice to see. But again, doing bar graphs like this, you can do before, and then you can do after, and do your graph there. Well, that might actually be better than doing something like this. Okay, so I'm pretending like I'm putting in those percentages, like 38. Maybe this is 29, and this is the 33 over here. So I'm doing that there, and I'm doing after the switch here. So something like that might actually be better than sticking with those pie slices. Okay, so other graphs. Well, here's another graph, and this is a bar graph. Okay, this is a bar graph where number of workers employed by major foreign investors by country. It's nice when they give the numbers up here. But if they didn't give the numbers, see how we can tell the horizon a little bit better? We can see this one is taller than this one. So even without these numbers, we could still kind of see. When you see a graph like this, where there's space in between, that usually indicates that there's no possibility in between these two categories. So you're either in Great Britain or you're in the category West Germany. You can't be somewhere in between. That's what that space is generally indicating. Now I say that with a caveat because not always will that be the case when people are presenting data. And it may be that there is assumed a continuum between bars and that you simply have to recognize that there's a continuum. For instance, if I take those IQ scores, well, maybe this is an IQ score of 90 and this is of 100, and theoretically anything is possible in between. Usually though, good graph makers will, in this case, attach these bars to show that there's a continuum. So that graph will look like this instead, rather than have that space, because IQ can be anything in between here. These situations are usually reserved for situations where there can be nothing in those spaces. Okay, but again, be careful, because if you kind of memorize that rule, you're going to come across graphs where people do not follow those conventions. You should be aware of it in general, though. Here's a nice way to present bar graph information. This is breakfast cereals in pounds and frozen foods by different countries. So it allows a direct comparison between the different countries, frozen foods in pounds, and you can come up with different examples than this. Maybe you can look at COVID-19 rates by country and look at different graph information. But this again allows for a bit of a horizon, right? You can see a little bit of horizon. So you can see that Ireland has more. You can see that United States has more over here. Then you can see as it goes down. But other than that, there's not much to know about bar graphs. Bar graphs or bar charts. Again, guidelines for constructing bar charts. If ever you need to construct one, there they are, but don't worry too much about it. Frequency histograms, relative frequency histograms. Just before that, here's an interesting bar graph. That's interesting because it separates the direct costs and indirect costs for the given year. So there's the total amount of money, and then it separates that money into how much is indirect and how much is direct. If you think of another, maybe we do the COVID-19, and then we put total deaths up here due to COVID-19, and then maybe we're separating it by comorbidity versus not. So maybe all of this is comorbid. There's a comorbidity, and for instance, people maybe have heart disease along with COVID-19, they have lung disease, etc. So maybe that makes up most of the deaths, whereas over here, there's no comorbidity. So we have this amount over here. That would be another way of presenting information using that bar graph, dividing it up idea like that. And again, you can come up with different ways of graphing information. It's not vital that you're like memorizing any of this. You're just kind of appreciating how different data sets can be presented in different ways. Okay, so let's produce some frequency data. So here's a frequency table for number of attached ticks in the book. Here's class 1, 2, etc. And here's the interval information. Again, you can read the example in the book, but these class intervals are made to help reduce the data down. So remember we said that at the beginning, we said maybe you have a whole bunch of data and you're trying to reduce that data down, right? Because you cannot interpret all of this information, okay? So we said, well, maybe you can calculate like a mean. Then we saw you can make a graph, etc. Well, here's another way of portraying the information where why are we reducing the data down? We're reducing it down to produce a more concise summary of the data. And the reduction occurs by using class intervals, okay? So again, you can look at the example in the book, but other examples, you can look at, say, grades, right? There could be a class interval for grade. So maybe 50 to 59, and then you have 60 to 69, 70 to 79, etc. Those are grade intervals there. And that is what makes up the class interval. So in this particular data, we're going from 16.25 to 18.75, 18.75 to 21.25, and we put the frequency of scores within that particular class interval. So there are two people who are in this interval. Notice how it's data reduction, right? We're losing information. Where are we losing the information? We're losing the information because we don't know what's happening within the interval. We simply know that there's 2 scores in there. And that's important because maybe those 2 scores are 16.25. Maybe both of them are 16.25, or maybe they're closer towards 18.75. We just don't know. Again, the idea of data reduction. There's a cost to doing that. We lose some information. We can compute the relative frequency, which is the frequency divided by the total number over here. So we can see here that relative frequency is 0.02. This is 0.07, 0.07, 0.14, etc. And that will sum up to the 1 over here, okay, for 100%. So again, what's the big picture here? The big picture is that when you produce class intervals, you're missing out on some data. But at the same time, you're getting a clear picture, right? Because look, you can tell right off by looking at this that there are 24 cases in this interval. So you can see where the majority of the data seems to be falling, seems to be towards the center of the distribution. Yet you cannot see those individual cases. Right? In the course, if I say, well, there's 10 people who are in this interval and there are 5 people in this one, you don't know. Is everybody getting 79? Is everybody getting 70? Notice that 5 people could be at 69 and 10 people at 70. Hardly any difference between the two. Yet this interval characterization would be completely correct. But still, you can't see what's going on within the interval. So there's the frequency histogram. Now it's a histogram. The bars are touching. So it's implied that there's a sense of continuity along this axis, right? There's a sense of continuity here. And again, that generally means that any scores are possible along this axis. It's not a hard and fast rule though, right? Remember that when we start talking about that, as we said, you're going to see different graphs where, you know, people can produce a histogram, yet it's impossible to have an observation between 2 different numbers. For instance, if we say, well, how many people go to rock concerts or something like that? So maybe you have people over here and you have all the bars, all the bars over there. Well, maybe this is 100 people and the next observation is 101. Well, you can't get 100.5 persons. So if this is 100 and this is, say, next to it 101, well, the bars may still be touching so long as we recognize that nothing is possible in between these things. Still, it's more convenient to make a histogram there than it is a bar graph. If we're dealing with many observations along this axis, we're probably not going to do this and then put one next to it and make sure there's a little space, right? Make sure that there's a little gap there. That would be overkill to do that. So the graphs or the bars are touching. Okay, so that distinction of histogram versus bar graph gets to be a little bit fuzzy, but generally continuity is implied along that x-axis. There's a relative frequency histogram for the tick data that we just looked at. And the histogram, we said bars are touching in general, implies continuity. Pie charts and bar graphs are used to display frequency data from qualitative variables. Histograms are appropriate for displaying frequency data for quantitative variables. That's a useful distinction to make between those bar graph and histogram ideas. What's a qualitative variable? Well, a qualitative variable is like the letter grade for the course. You're in this category or this category, but you're nothing in between. That's generally what's denoted as a qualitative variable. Here's another example of a qualitative variable. Brown hair versus blonde. That's a qualitative variable, hair color. Now, if we think of quantitative variables are like those IQ scores, where it's assumed there's some kind of a numerical continuity, 70, 71, 72, Anything can happen between 70 and 71. It's a quantitative variable. It's measured on the numerical scale. Blood pressure would be quantitative. Weight would be quantitative. Height would be quantitative. Whole bunch of variables like that. Again, though, when we really kind of crunch these distinctions, we get into a lot of trouble because look, if I do this 1, 2, 3, 4, 5, and I call that your pizza preference. How much do you like pizza? Do you like it a lot? Or do you like it only a little bit? Well, what is this? Is this a qualitative variable or is it a quantitative variable? It becomes really hard to make those slight distinctions, right? Because is any score possible in between here? Probably. Yet I'm only asking you to circle 1, 2, 3, or 4, or 5. So that could actually be regarded as either. Simply because the variable uses numbers does not always mean that it's quantitative. It could still simply be denoting qualitative categories. Okay, book talks about probability here. We will be talking about probability a lot as we go on. So you can read what the book has to say there, but there isn't that much information, and we'll wait until we talk about probability. Okay, more graphs, more plots. Well, let's look at some of the shapes here. Here's some shapes of distributions. Now, when we talk about distributions, let's be sure of what we're talking about. A distribution implies that there are different scores, right? So if I take these scores here, 55, 55, though I can call this a distribution, it's not really the intended meaning behind distribution, right? This is a distribution, but the score is a constant. They're all the same score. When we talk about distributions in general, we're using the term because it implies that there are different scores in the data. And we want to see how those scores are spread out. That's the idea of calling something a distribution. How do the scores distribute themselves? But in this case, we could still call this a distribution. It's just it's a boring distribution because everybody has the same score. But again, the intended meaning is that you have a lot of different scores. You have variability in your scores. So in this particular case, we have a uniform distribution. Generally, it's uniform. It's not perfectly because it goes up and down here a little bit, but there's no special shape to it, to the uniform distribution. It's kind of rectangular that way, right? Looks like almost everybody's getting about the same score. So it's generally uniform. This one here is a symmetric, unimodal, and as we'll see, a normal distribution. So it follows this kind of bell curve shape over here. It's symmetric. What makes it symmetric? Well, it's approximately symmetric. If I cut it in half, this side is a mirror image of this side. Again, this is not a perfect distribution. Notice that those bars are not the same height. So this is an approximation of symmetrical. It's definitely unimodal. It only has a single mode up here. So the most frequently occurring score is around here. If I had a distribution where those bars were like this, well, then it's not unimodal because we have two categories having the same frequency over here. Okay, so generally the unimodal distribution will have that single peak to it. And as we'll talk about later in the course, it's a normal distribution, and that's just the shape of the distribution. It has that nice bell-shaped curve. Oftentimes when we think about a distribution, we think about things that look like that, nice bell shape. Well, here's a right skew distribution, and this is sometimes called a positive skew. Notice that the positive skew has scores going out to the higher end, and most of the scores are on the lower end. If you look at the left skew, it's the opposite to that. We got a lot of high-end scores here, and then they trail off into the lower end of the distribution. Well, there's the bimodal distribution. Okay, that remember we talked about the unimodal up there? Well, here's the bimodal right? I have one mode over here and one mode over here. What distributions are bimodal? Well, if you look at math scores in high school, sometimes those can be bimodal because you'll have one group of students who are not grasping the material, and then you'll have another group that are. So if we look at grades, 100, say to 50, sometimes that shows up in high school math scores that this group is not getting it, whereas this group is. Bimodal distribution, left skew. Well, here's an interesting situation, right? We have a little bit of a hump of scores here, but then we have another mode going on over here. So we have some left skew, but we also have a few scores over here. And that can happen sometimes. Sometimes that can happen in data where these observations, maybe there's a peculiarity about these observations that didn't seem to follow this particular trend. For instance, if you think of a situation like this, you might think of education years. Okay, in general, I believe it's true that the more years of education you have, probably the higher your salary. So you'd expect more of the scores over here. But at the same time, we also know there's many people who have no education that are doing very, very well. So that may be represented over here. Okay, so a lot of distributions that could have that shape. Okay, stem and leaf plots are for describing data, and they generally work like this. Let's look at this raw data. Well, there's a score of 60, there's a score of 61, 61, 64, and these are ozone readings. So imagine we want to plot this data. We can use what's called the stem and leaf plot. So how does the stem and leaf plot work? Well, you can figure how it works. Look, where's the 60 go? Well, the 60 is right over here. There's the 60. Where's the 61? There's two 61s and they're indicated right over here. So notice that the stem and leaf plot is taking the first position here, and then it has the trailing position over here. So it's representing that 6, 0. Okay, that's how that stem and leaf plot is working. And they don't always look this way. Sometimes if the numbers are really big, you may have the stem be a lot bigger than the leaf. But in this particular case, and in general, they work like this. So what's the advantage of looking at the stem and leaf plot? Well, you can look at all those stems, and then you can look at all the leaves, and you can get kind of a picture of what the data look like, right? You can look at, if you tilt it, if you rotate it, you can actually see the skew there a little bit. One advantage of looking at a stem and leaf plot is you can actually read the data points in the plot. So look, see all the 71s here? I can see all the 71s right here. Notice that if this was a bar graph and I simply had a bar representing the 7 here, I wouldn't know what's in here, right? So if I put this on its vertical like that, I wouldn't be able to tell what's inside the bar if that's a bar graph. But with the stem and leaf plot, I can actually read the numbers. That's what's key to the stem and leaf plot. You can think of it almost like a naked histogram, right? Because the histogram, you can't see what's inside here. Whereas in the stem and leaf plot, you can actually see those numbers. Okay. So stem and leaf plots are useful for plotting data and getting the sense of a distribution. Again, guidelines, you can read through those to help you understand what the stem and leaf plot is about, but definitely you do not want to be like memorizing this, and you will not be asked on the test to go through the guidelines for constructing the plot. But if it helps you in understanding what that stem and leaf plot is communicating, then definitely be sure to read over that. Here's some more data. So I've circled the 326s here because I'm going to try to find them in this plot over here. So where are they? There it is. 326s. right over here. Okay, so if I look back at this, well, am I missing one? Where's the other one? It's got to be somewhere. So I've got 326, 326. Do I have another one? I can't find it right now. Can't see the 326. Well, let's start with the 317. Maybe I just can't see it right now. There's a 3-1 and there's a 7. So there's the 317 right over here. There's the 317. Let's look at the 318. Do we have a 318? There it is. I just can't see the 326. It's probably in there. Or else this isn't the complete data set. But anyways, that's how you read that off in terms of looking at the stem and leaf plot. Notice that in this particular case, how this plot differs from the previous plot is that in this case, the leaf unit is equal to the unit position, right? So it's 317. They're the units over here. So you got the tens, the hundreds. This is what's corresponding to the leaf in this particular case. That's why it says the leaf unit is equal to the 1 position. Again, when you read the plot and you look at the data set, you can match those things up and you can generally see what that plot is communicating. But that's why I said that the stem and leaf plots will be a little bit different depending on the data set. You know, over here, we had the same idea, right? We had the same idea, but we had 61. You can just read the 6 and the 1 off there. Whereas here, there's only the 1 position right here. There's only, there's only the 10th position here. There's the unit. So you see how the plots are a little bit different. And when you look at more in stem and leaf plots and more complicated situations, they can get kind of involved and you have to kind of read how the software is actually communicating that leaf unit. Okay. Usually it takes about 2 seconds to kind of see what that plot is actually producing and then you're fine. Okay, I think that's about it for today. A brief note on time series. You can read that over if you like. And time series is just putting time on this axis and some measure over here. So this is yearly total violent crimes across time. So it looks like there are a lot of violent crimes in this period, but then they were brought down over here. So those are interesting graphs where you connecting the dots over here and you have year on this axis. So that's what makes it the idea of a time series, because you have time on one axis. And oh, here's the interesting plot of the Dow Jones average. So if you invest in the stock market, these charts are of interest to you. They plot that Dow Jones average over time. And again, it shows you the ups and the downs and the peaks and the valleys and quite a peak over here. So there was the economic crash recently due to COVID. So, you might have had the plot like this and then you see the big drop and then it's kind of coming back up. This happened in about March where you saw that big drop. So those are useful plots as well. And you can have a read of that for more plotting. And again, don't worry too much about the guidelines. We're purposely going through these graphical ideas relatively quickly. You notice that we're not focusing too much on the details of how to construct these things because we have more important things to get to. And that's going to start on Wednesday when we talk about measures of central tendency. So again, what did we talk about today? We talked about how to plot information. We talked about histograms, bargrams, pie charts. And generally, as you're reading through that, you're getting a good feel for how these things are done and different methods of representing data. We also talked about the idea of reducing data. So Be aware that when you reduce the data, there's a cost to reducing it. You're losing some information. That graph of the stem and leaf plot was kind of interesting because you can actually see the data points within the plot. So again, you're not memorizing this stuff. You're just getting a feel for how data is presented. Now, on Wednesday, we start talking about these ideas of central tendency. And this is where we're going to start talking into the numerical formulas. We're going to start presenting numerical formulas. And there, we need to spend a lot more time on. So Wednesday starts to get a little bit harder as we go. And Wednesday, we look at some formulas. So we got to really understand how to compute measures of central tendency, but also what they are telling us of our data. Okay? So that's it for today, and we will see you on Wednesday.